from Brussel, we'll talk of Braided and the progress of dynamical.
Thank you very much, and also I would like to thank the organizers for organizing this very nice workshop. I will be speaking about joint work with Canada Comer. Okay, so I'd like to start with motivation. Why do we need this object, which I will call Braided as a product? So let's start with classical locally compact group, so usual group, and let's say it acts on two von Neumann algebras M and N. So that we are on the same page, by action of a classical group on a von Neumann algebra, I mean homomorphism from G to the group of automorphisms of M, so invertible star homomorphism preserving unit, and I put the following continuity condition, namely for each M, the associated map from G to M is supposed to be Weak-star continuous. Then it doesn't take too much of work to show that there exists a diagonal action on M tensor M. Namely, clearly for each G, we can take tensor product of homomorphisms, alpha M and alpha Ng, and then a small argument shows that this is indeed still appropriately continuous. So, natural question is similar construction, does similar construction hold in quantum setting? Namely, if we have action of locally compact quantum group, do we get some kind of diagonal canonical action on tensor product? And the short answer is no. Later on, I will make this a little bit more precise and actually show a simple example where it fails. But it turns out that we will get a canonical action if we change circle to the square, which I also will introduce. Okay, I think my talk is the first one on this conference where I will be speaking about locally compact quantum groups. We have seen a lot of compact quantum groups, discrete. So let me give a very brief introduction to those. So as a form of motivation for the definition that I will quote, let's still consider classical locally compact group. Then we have a von Neumann algebra of measurable bounded functions. Multiplication in a group after pullback gives rise to co-multiplication, which is a map from L infinity of G to its tensor square. And we also have Haar measures, which give rise to integrals which can be seen as weights on this von Neumann algebra L infinity of G. And they are appropriately invariant. Now, with this reformulation, I believe the following definition proposed by Kustermans and Vaz is quite natural. That locally compact quantum group consists of a von Neumann algebra, normal unitary star homomorphism from this von Neumann algebra to its tensor square, which satisfies this condition, which is called co-associativity condition, and by assumption there exist two weights which satisfy appropriate invariant left and right invariant conditions. Because I won't use them directly, I didn't spell it out. And because I want to be fancy, I will use this. I will use this suggestive notation where I write L infinity of G for M and then the L1 of G for the pre-dual. Okay. So let me maybe say that I have given you von Neumann algebraic definition because I want to work with von Neumann algebraic actions, hence it's quite natural to start with this. Equivalently, you can start with system algebraic definition and arise at the same object. These two approaches are equivalent. And compact quantum groups, which I believe should be more familiar, fit into this framework, maybe with some caveats. But then one can recognize that G is compact precisely when, let's say, left Hare integral is a state. After normalization, so it is bounded function. Okay, very nice feature of this theory of Kussmaul's and Vaz of locally compact quantum groups is that with any quantum group, one can associate its dual locally compact quantum group, which is denoted G hat, in such a way that when we take second dual, we get back to the original quantum group. So in this sense, within the framework of locally compact quantum groups, we can extend Pontryagin duality of locally compact abelian groups. With this, we can really define discrete quantum groups as duals to compact quantum groups. This isn't the only way to define discrete quantum groups, but it's a possible way. And then it turns out that we can see that the von Neumann of functions on a discrete quantum group is a direct product of matrix algebras, which corresponds intuitively to the fact that the underlying quantum space consists of isolated points. They are quantum, which is which correspond to the fact that we have matrices. Okay. And there is lots of examples of compact quantum groups that should be, at least some of them should be quite familiar. The famous SUQ2 example of Voronovich for quantum information. Quantum permutation groups are very important, but we have also more fancy examples like Q deformations of compact semi-simple simply connected Lie groups. There are also free versions of quantum versions of orthogonal and unitary groups. Okay, what about locally compact examples? Well, as you might expect, every locally compact group should give rise to a locally compact quantum group, and this is indeed true. And the construction is very natural, at least if you don't go too much into technicalities. Then with with locally compact group G, you can associate quantum group blackboard G, where the objects that you look at are as here prescribed. And then this quantum group, typically one can identify it with G itself, and this class of quantum groups are called classical. But we can also, starting from a locally compact group, we can construct another quantum group, whereas the von Neumann algebra functions on this new quantum group. We take group von Neumann algebra, and then you can show that there exists a multiplication which on generators act as prescribed here, and as weights you can take the Plancher weight, and this also gives rise to a locally compact quantum group, which turns out to be dual to G in the previous sense. So in a very short time, I will give you more interesting examples. We want to speak about action, so as usual, let's first think for a moment about this classical situation. When classical group G acts on M, and let's say everything is separable, then we can associate map alpha M, which goes from M von Neumann algebra to functions from G to M, simply by applying alpha G to M. And the algebra of functions from G to M can be identified with tensor product. So with this reformulation, again, the following definition should be quite natural. Locally compact quantum group acts on a von Neumann algebra when we have such a map, unital normal injective star homomorphisms from M to tensor product of infinity of G to M, which satisfy this condition. So this condition really corresponds to the fact that we act by that the classically, the map from G to automorphism is a homomorphism, so we have actually an action, and continuity is already taken care by the fact that we work in this tensor product picture. And I will write this by this nice arrow notation. So there is a lot of examples, two easy examples to keep in mind. On any von Neumann algebra, we have trivial action, where every m goes to one tensor m. And when we think about classical situation, one tensor m really is the function, the constant function, which at each point of group gives you the same element m. So this is justified the name that this is trivial action. But a little bit more interestingly, whenever we have quantum group G, we can take as the von Neumann algebra L infinity of G, and we have comultiplication, which gives another action. Then this action condition really turns into associativity condition. So every locally compact quantum group acts on its function algebra, and this classically this is really the translation action. So maybe a small comment: when we speak about actions of classical groups, there is really no way of distinguishing between. Okay, what do I want to say? That whether we here put an infinity of G to the left or the right really is kind of a matter of convention, and this gives rise to the notion of left action, right actions, but really there are canonical ways of translating between them. So this isn't too much of an issue, and I will work with left actions. But you can always pass canonically to right actions from left. Okay, so now I will give you the easy example where there isn't there is no diagonal action on tensor product. So as the quantum group, let's take dual to free group on two generators. This means that L infinity of G is the group von Neumann algebra of F2. Comultiplication acts in this way. And we consider translation action on the group von Neumann algebra of F2. And then, what do I mean by the statement that there is no diagonal action on the tensor product? Well, we have canonical embeddings from M to tensor square, or simply by tensoric by 1. And I'm saying that there is no action on the tensor product such that embeddings are equivariant. And this is really easy calculation. So let's say that there is such an action, and let's look at this element. Lambda A tensor lambda B can be written as product of embeddings. Then we use that alpha m is multiplicative, so we can split this product. Next, we use the fact that the assumption that embeddings are equivariant, which means precisely this equation. And then when we clean it up a little bit, we get at the following expressions. But we can also write the same element in another way. We can write this product in different order. And then when we do similar calculation, we arrive at lambda AB different than lambda BA, which is contradiction. So clearly in this situation, there is no diagonal action. Okay, so now I will go to the construction and definition of braided tensor product. So for this, I need a little bit more structure. Namely, I will be working with quantum groups which are so-called quasi-triangular. This means that they come equipped with a unitary R hat, which is a unitary in L infinity of G hat tensor square, satisfy three conditions. Well, the first two conditions are compatibility with multiplication, and then also adjoint by R turns multiplication to its opposite. And such a unitary is called R matrix. This is a piece of terminology. The first two conditions means that R hat is a bicharacter. two examples. Well, whenever we have, first rather trivial example, whenever we have classical locally compact group, we can take trivial unitary as the R matrix and everything will work. More generally, if this group is abelian and classical, then you can really take any by character. This will give you a little bit more larger family. But for us, most importantly, will be this second example, namely that Drinfeld double, which I will define shortly, always comes equipped with a canonical R matrix. So maybe you don't need to remember this structure and this definition. The point is that we will be working with quantum group equipped with extra structure, and Drinfeld doubles are such quantum groups. So what is a Drinfeld double? This is a very nice construction, general, which allows us to get easy examples of locally compact quantum groups with intricate structure. So let's start with locally compact quantum group, arbitrary quantum group H. Then there exists new quantum group D of H. As the von Neumann algebra, we simply take tensors product of L infinity of H and L infinity of H hat. H hat is dual quantum group. It comes equipped with its own von Neumann algebra. We can take tensor square. And the commultiplication, as a first approximation to commultiplication applied to X, we apply commultiplication of H to the left leg, multiplication of H hat to the right leg, and we apply flip to legs number 2 and 3 so that we land in the appropriate space. But if we stopped here, we would simply end up with the definition of product of H and H hat. So this wouldn't be too interesting. And what you do is you twist by a certain unitary, namely the Katz-Takesaki operator. I won't go into definition of this operator. It's canonical unitary which you construct for every locally compact quantum group. One way of thinking about it is that it really is the left regular representation when interpreted appropriately. And for this construction, it means that it, in a sense, introduces non-trivial interaction between H and H hat. One can show, in this context, I believe it's due to Bashvas, that there exist appropriate Haar integrals such that so that D of H really is a locally compact quantum. And as I claimed, whatever H is, D of H is quasi-triangular with R matrix given by such a formula. And again, it won't be too important for us what exactly it is. So let me just say that it is constructed out of Katz-Takesaki operator for H, embedded into appropriate space using maps which mean exactly that H and H hat are closed quantum subgroup of Drinfeld double. You can give a concrete formula for it, but it isn't very illuminating. So for us, it will be enough to accept that it's a canonical R matrix constructed out of the structure, and that we already have. Okay, so at least we know that there is a lot of interesting quasi-triangular quantum groups that we can work with.
Excuse me. Yes. Does this construction give you if you start with a normal group, classical group?
So if the classical group is abelian, then it will be simply a product of the group and its polytriangle dual. But if it is non-abelian, you will actually get an interesting quantum group. So yeah, that's a good point. It's actually also a good way of getting quantum groups out of classical ones. All right, so now let me define a braided tensor product. So the setting for now is that we have a quasi-triangular quantum group which acts on two von Neumann algebras M and N. Next, and we define a braided tensor product as a closed linear space sitting inside operators on HM, Hn. So our von Neumann algebras are represented on Hilbert spaces HM, Hn. And this linear space is generated by products of this form. So we have two embeddings. Iota n is embedding of n inside this braided tensor product simply by putting n on the second tensor leg. So nothing too interesting. Iota m is defined by as follows. So we put m also on the second tensor leg, and we conjugate by flip operator. So this symbol is flip operator. If I stopped here, if the symbol was simply the flip, I would end up with usual tensor product. So that's why we don't stop here. And the this operator, which is called we can call it braided flip operator, is flip composed with certain unitary, which is built out of the R matrix and our actions. Maybe let me write a little bit more. What do I mean by this? So we have an action of G on M. And I want to use implementation of the action. So what do I mean by that? So alpha m of m is an element in L infinity of G, tensor m. And then implementation of action is a unitary, such that this action can be written in the following way. Furthermore, U is a representation. So this means that U is a unitary in L infinity of G, tensor B of Hm, and when we apply commultiplication, we have compatibility with commultiplication. Then, general theory of that was developed, let's say in this context by Neumann, allows us to write this unitary representation in the following way. So we again have Kac-Sakisaki operator, and to the second leg we apply map phi n, which is a map from, well, C0 of G hat to B of Hm. And for reasons that I won't go into, we have universal lift. So the point is that Stefan Vaz proved that there always exists an implementation, which means that we get a representation which implements action in this sense. Out of representation, we get star homomorphism, phi m, and this phi m comes into the definition of braided flip operator. Okay, so the message from here is that we have definition like for tensor product, but the flip operator is twisted by a unitary which comes out of the action and out of the R matrix. A terminology that I won't follow, or the notation that I won't follow, but it's maybe good to think about, is that this product of embeddings really should be thought of as braided tensor product with elements. And I should also mention that similar work in system algebraic context was developed, or similar construction was developed previously by Roy Voronovich. Though the proofs that they write don't really most of the proofs don't really translate to von Neumann setting. But previous in system setting, similar work has been done. Also, maximal version by Roy and Timmerman. Okay. So, out of quasi-triangular quantum group acting on M and N, we define a closed linear space, and we have these two embeddings. So first result that I want to mention is that Braided tensor product depends on actions and R matrix, but does not depend on representations. So a priori, the definition really uses it, but if we choose different representation on different Hilbert space and different representation of action, which is not unique, then we would get isomorphic object. In a very strong sense that really also generators will be mapped to generators. And okay, so that's one nice property. And less trivial observation is that the space actually is a von Neumann algebra. So it at all isn't obvious by definition because it's only defined to be closed linear space. The problem is that so we need to show that it's invariant undertaking adjoint or products equivalently. And if I have time, I will say more about it at the end. For now, let me just maybe say that first one does it for dual actions and then use biduality theorem to reduce to dual actions. Okay, maybe as a side remark, to which I won't go too deep, the construction and really the setting that we work is more general, where we don't have maybe R matrix, but just a bicharacter, and then a lot of the properties still hold, not all of them, and it gives more flexible definition. But for the sake of this presentation, mostly I will stay with R matrix. Okay. So as I promised you, whenever we have braided tensor product constructed out of R matrix, we have unique action of the quasi-triangular quantum group on the braided tensor product such that the embeddings are equivariant. And it actually is quite concrete in the sense that when you choose implementations, then the action on braided tensor product also is implemented in kind of the obvious way. So you really could guess it. So work needs to be done to show that actually this injective star homomorphism defines you an action. And conceptually, at least in this setting, what is behind the proof is the fact that a category of representation of quasi-triangular quantum group is braided monoidal using these braided flip operators. Okay, so you may wonder, well, how do you find actions of quasi-triangular quantum group? So really the example to keep in mind is the Drinfeld double example, and then action of Drinfeld double amounts to action of quantum group and its dual on M, which satisfy certain compatibility condition in the Drinfeld condition. Okay, maybe a comment. We get a little bit more general version of this action, where maybe you don't start with R matrix, but it isn't the case that you can take arbitrary bicharacter. Okay, so we have this action. Next, I want to present some properties and examples. So, trivial examples to mention. If action is trivial or R matrix is trivial, then the braided tensor product is isomorphic with the usual tensor product. That's not very surprising. What is not that obvious, though not too difficult, is that if one of the actions is inner, then you also have this isomorphism. However, for some time we were trying to prove that more generally, if action is that the braided tensor product is, okay, maybe let me put it another way. Interaction means exactly that the action that you work with is cocycle conjugate with trivial action. So you may ask more general question if braided tensor product stays invariant under taking cocycle conjugacy, and this turns out to be, we don't know, it's not clear. The definition, the construction for cross products really does not. Okay. More interestingly, when we take as this more general situation and as a bicharacter we take a Stakisaki operator, and as one action we take action of G on M, arbitrary action on, action of arbitrary locally compact quantum group on von Neumann algebra. As the second action we take translation action of L infinity of G hat. Then we can construct this kind of braided tensor product, and quite easily it turns out that it is isomorphic to the cross product. So this gives us a lot of examples. In particular, we can take as M L infinity of G and as action translation action. Then it's well known that the associated cross product is isomorphic with B of L2. So when you start with appropriate quantum groups, you can cook up in a not too difficult way examples where you take braided tensor product of type 2 or type 3 infinite von Neumann algebra, and in the result get type 1 von Neumann algebra, which is really something that does not exist for usual tensor products. And the examples to take here are either you can start with compact one and take, let's say, product but by the dual, or let me also mention a very nice work of Vrije, where he constructs locally compact quantum groups such that both L infinity of G and G hat have this type and are factors. Okay. Another quite easy example that we get here. It's well known that discrete group SL2Z is weakly amenable, but its semi-direct product with Z2 is no longer weakly amenable. And using this property, you can quite easily get an example where braided tensor product of von Neumann algebra satisfying weak star completely bounded approximation property won't satisfy weak star completely bounded approximation property. And also, a result that we learned from Stefan Bass is that, again, using this isomorphism with cross product, you can get example where braided tensor product factors give you non-factor. Actually, you can get here diffuse center. Okay, some more properties. Well, quite expectedly, you can take braided tensor product of maps, but we have to be a little bit more careful. Namely, if we assume that, well, rather obvious condition that we want to put in this context is that our maps are normal and completely bounded. So these are two conditions that are quite okay, but we can get braided tensor product of maps if we also assume that they are G equivalent. Then braided tensor product of maps exists, and we have some expected properties, being completely positive, being homomorphism, being completely isometric is preserved. Shortly, I will show that this condition of being G equivalent cannot be dropped, which is, at least for me, was a little bit more surprising. Okay, as a quite easy corollary, you get permanence properties for approximation properties. More precisely, if your von Neumann algebras have one of these three approximation property, we start completely positive approximation property, completely bounded or operator approximation property, and you assume that maps are equivariant, then M tensor N also has this property. So that's really rather easy corollary. Maybe in Wixar OAP case you need to work a little bit harder because things are no longer nicely bounded. So
didn't your slide 2 slides ago give an example where this didn't work for Wix? Because you didn't.
But here you don't have equivariance.
Ah.
So combining these two observations shows that you will get here net implementing Wixar CBAP, just not equivariant. So this equivalence condition is quite important. Okay, I don't have too much time, so let me just, well, not go into details of this construction, but looking at R as our group, and the following R matrix, by looking at rotation actions, you can cook up an example where braided tensor product of functionals does not exist. So first, when you simply take braided tensor product of infinity of t, you get something which means that, well, braided norm changes a lot, and then passing to infinite tensor product, you can blow it up so that you can actually show that you cannot take braided tensor product of functions. Okay, because I'm running out of time, let me just mention that braided tensor product depends on the order, which maybe isn't too surprising. Another thing that I will go very quickly through is that there exists infinite braided tensor product, and in the remaining 2.5 minutes, let me sketch proof of the theorem that M braided tensor product N is a volume algebra. So the first, the proof is done in several steps. And the first step is we prove the claim under additional assumption that our action is dual action. So in the setting of quantum groups, when you can take cross products, and you will get a dual action on this cross product by quantum group opposite to the dual. And it is, well, there is a concrete formula for it. So why does it help us? Well, if you assume that one of the factors in braided tensor product is dual, you get more information about the generators of this. And what you really want to show, well, is some kind of commutation relation. When you have more information, it is easier. So we have two, as we see here, we don't? Well, we have two kinds of generators in cross product. One are the generators coming from, in the situation, n tilde. And then, you can show that really this generator commutes with generators coming from M. So you have nice commutation relation, trivial one. If you take second commutation, if you take second generator, then you then you need to work harder, but you can also prove that there is form of commutation relation. And maybe a nice ingredient to mention here is that during it you use action of G hat on M built out of action of G on M and your R matrix. Okay. And okay, so this is first step. Then using biduality theorem, you reduce the situation to the case when one of the factors is cross product, and you have dual action. However, for those who know this construction, it gets a little bit complicated by the fact that cocycle appears, and you need to work to get rid of this. And I would like to end here. Thank you.
questions?
This braided tensor product, is it associative?
Yes. Or yes. So let me be more precise. The short answer is yes, in the situation where you start with R matrix. Because really, to speak about associativity, you need to have some kind of action of your group on braided tensor product. This action exists when you start with R matrix. When you start with arbitrary bicharacters, speaking about associativity doesn't really make sense. However, we actually get a little bit more general statement when you start with when you maybe not act with your quasi-triangular quantum group, but certain canonical subgroups of it, which in the case of Drinfeld doubles correspond to H and H hat. And then you have also generalization of this associativity statement.